My name is Richard Henry, and you're listening to the COVID-19 Challenge podcast. COVID-19 is a disease state caused by SARS-CoV-2, which is this novel virus that popped itself out of China over a year ago now. The virus actually causes an acute reversible ACE2 depletion in humans. That is how this virus makes us sick. Most humans don't actually get sick, overtly sick with this virus. It's really just a cold virus, but it says, and we've evolved to live with coronavirus cold viruses. In fact, we don't even maintain lifelong immunity to the virus when we catch it. With, say, a measles infection, there's lifelong immunity, but our immune system doesn't even seem to waste immune memory or memory space on this virus. We get infected every couple of years, we kill the virus off, and we move on, having only got a mild illness. So only about 10 or 20% of humans get, even though they're sick with this virus, and less than 1% or even 0.1% die. So understanding COVID is really about understanding ACE2. As ACE2, the protein that the virus really depends on for its survival and its replication, is really the way of explaining this whole pandemic. It's key to really understanding it and also winning. So whenever you hear people talk about we just don't know enough yet, attributable to this disease and how it works, and that it's multi-system, it's because they've left out the key part, which is understanding ACE2. The other coronaviruses don't target ACE2, except the last two main ones, and that was COVID-1, which showed up in 2002 and caused SARS, and now this new one. So let's just pause here for a bit and go back. What is a virus? It's a piece of shareable genetic code. It's a very few pieces of code bundled up together and encapsulated in some way in order to be transportable from host to host. So let's just stay with viruses in humans to keep it simple. So the virus encapsulates itself just before it leaves the cell in which it's replicated itself, and then eventually it needs to be transported either to another cell in the same body for further replication, or eventually to get out of that host into a new one. If it just stayed in its single host, then it would die with the host and there would be no survival of that virus. SARS and COVID-19 are viruses that spread through our breathing. So it's respiratory spread disease, so the virus goes into our airway and our lungs and comes out the same way, largely. It gets breathed and coughed out in little droplets of fluid that come out of our lungs, always. And these droplet sizes are variable, from very, very minute that can stay floating in the air for a long time to large gobs of mucus, which would have more virus in them. The trick for the virus is to get from one host to the next, and so in fact another human has to just take in those droplets from the person next door to them, and the virus gets in. And this is really the key behind what we now call social distancing and mask wearing, right? So we're trying very hard to stop the spread, and then also cleaning up in between us with washing hands and all sorts of sprays to try and kill whatever virus is out there. Although the virus is encapsulated, it doesn't really last long, and particularly doesn't do well in sunlight. You almost think of them as little vampires that die as soon as they see the sun. Now, we're going to start with the virus entering its new host. So it's got to get into entry into the host, which in this case is through the airway, through the nose, and through the mouth, and down into the trachea and lungs. And then it has to find a hospitable cell that would allow the virus to enter into the cell. So viral entry is gross. In the gross term, it's got to get into your body. You have to ingest it or breathe it in. And then it has to actually enter a cell. And it's this entry system and entry mechanism that really defines viruses. And that's why viruses also don't spread necessarily between different species, because the entry system that works in one species may not work in a different species, because that protein, although it does the same job, may not actually be identical and identical enough for that virus to cross over. So whenever we talk about viruses, we'll also look at the target species in which it is able to enter those cells. So the key issue is viruses don't just walk in, they've got to get past a number of different barriers. These barriers are gross barriers, as in turbinates in your nose, all sorts of cilia and mucus in your airway that will sort of catch those particles and then immobilize them and cough them back out again. So these we call physical barriers. And it's often only the very small particles that can get past those physical barriers and down into the air, into the air sacs in your lungs, into the alveoli, right? At this level, the alveoli surface cells are making a set of proteins called surfactants, and these surfactants are designed to destroy all viruses. In fact, they destroy viruses, bacteria, fungi, and they're almost a smorgasbord of antibiotics, antiviral proteins that immobilize and destroy invading pathogens. There are also proteases that can cut up the protein envelopes of these viruses and render them unable to enter cells. So for a virus to get in, it has to get past a number of different defenses, and then it's got to find its host cell and find the entry protein, which is almost like a locked door, and it has to have a key to get into that door. Now, humans express this ACE2 protein in our airways, in our nose, in our lungs, and many other parts of the body. We're going to come to that later. But ACE2 is actually a door for these viruses, and it is situated in cells right where the virus gets in. The virus needs to somehow interact with ACE2 to allow it to cross over the cell membrane, which it's unable to cross on its own. So in this case, COVID-2 actually is opened up by a protease that is designed to kill the virus, but COVID-2 has sort of evolved so that the protease doesn't actually kill it, but actually opens up the protein, the so-called spike protein that binds to ACE2. So it opens it up and allows it to bind very strongly. It's almost like it pulls off its armor, and the virus opens its jaw and clamps onto ACE2. These are two protein sequences that are designed to fit like a glove, and it's this beautiful, strong physical and electrostatic fit that makes the virus so formidable in finding and opening the door to get into the cell. So in doing this process, ACE2 also gets cleaved, gets cut open as well, and the outside piece falls off, and the membrane piece tries to retract and save itself and go back into the cell, but it actually pulls the virus with it. This is a very beautiful system if you're a virus maker, and it's actually over 100 times more efficient than the first iteration of this coronavirus, which caused SARS. And so we now have a virus that's a lot more potent. You need a lot smaller dose to get that first critical entry into airway cells. In our attempt to try and block this, we're using masks and social distancing, and it's can be quite complicated, and it's beyond the scope of this talk as to what sort of strategies you need to get those very small droplets from passing from one person to the other. Now, once that virus is inside the cell, it needs to replicate. So once it's safely inside, it then fully undresses. It takes off its protein coat and discards it. Now that protein coat can set off the alarm bells to the cell itself that it's been invaded, and we'll come back to that in a bit. But the virus does better if it can stay in stealth mode and not wake up the guards inside the cell. Our cells are constantly watching for foreign proteins, and they quickly will dispense of any foreign proteins that are found. So CoV-2 then undresses and allows that sacred RNA code to find its way into the protein processing unit called the Golgi apparatus. This apparatus reads code for a living, reads RNA code, and churns out proteins according to that code. And those proteins that are churned out are actually components of the new virus. So the virus then deconstructs itself, runs the code through a Golgi apparatus, and makes hundreds of or thousands of copies of itself, which are then assembled by the protein assembly unit called the endoplasmic reticulum. It's then coated with those special viral proteins, and as the virus is then exported, so it goes to the cell membrane and is kicked out of the cell in the hundreds of thousands. By maintaining stealth mode, the virus gains valuable time to replicate and get out. And in terms of this pandemic, one of the hallmarks is that when people do get infected, they often don't know. They start replicating the virus and spreading it without getting any symptoms of inflammation, which is the war against the virus. So the virus maintains stealth mode. In order to do this, it's actually been equipped, or has equipped itself, with a protein system that can shut down the alert mechanism. All of these proteins have names, but their names really aren't relevant, other than that they do exist, and this virus is capable of doing just that. Now, the new virus then leaves the cell in its thousands and moves along through just diffusion to other cells around, and each virus will again look for that entry protein and just follow nature's course and replicate itself. And so the virus can spread through tissue locally from cell to cell, but it can also get into some of the travel routes around their body, be it lymph fluid, or most commonly blood, and then spreads out through the whole body using blood and using the circulation. Remember that virus is always hunting out those entry proteins and will so-called attack or enter those cells whenever it finds them. Again, this is not a conscious effort, it's just biology. The more ACE2 expressing cells that we have in our body, the more cells, the more breeding cycles can occur, and the higher the viral load. In other words, the more viruses you produce, so you literally become a breeding ground for this virus if you have a lot of ACE2 expressing cells, or a lot of cells expressing a lot of ACE2. The cell can cycle back in and round and round and round, replicating itself. Once the immune system realizes that there is actually an invader, it starts to respond, both intracellularly, where it will make proteins that will try to destroy the virus. It'll also send out a stress signal to outside the cell, which will then activate the local guards, which is the innate immune system cells, which will then send out an alarm, which we call inflammation, and other white cells come running or get attracted to the area and start to try to destroy the virus. They'll also, some of the cells will try and decode the virus by making antibodies, which are proteins that will bind specifically to the virus coding and immobilize it. So they're literally making handcuffs in order to catch the virus and then enable it to be incarcerated in a cell, in another cell, which then eats it. If at times a cell is overwhelmed with infection, the body has the ability to literally destroy the whole cell, and so it'll blow up the cell, and that cell is then destroyed, and the debris the leftover is carried away. I don't want to evoke too many thoughts about warfare and things that humans do, but this really is protein warfare, and it's the host organism trying to keep itself clear of all non-self proteins, which is really one of the hallmarks of self-defense. So at this point, we've got two viral strategies. One is for the virus to get inside a cell and go silent. So once the immune system kicks in, some viruses have the ability to go silent and hide and become dormant. And in that case, the host then becomes a carrier. And the other strategies for most of the viruses to escape and get out of that body and find a new one that hasn't been alerted. And in the case of this virus, it doesn't seem to go dormant, or we have yet to find out, but it does escape and spread into new hosts even before the immune system has been alerted. This is what is making it so difficult to contain this pandemic. It's the silent spread, coupled with the fact that many people get go through the whole infection barely knowing that they're sick. So those are fairly strong confounding issues that may make it that we can never contain this pandemic, and that this virus is going to become endemic in humans for the rest of time. Now, for a virus strategy to work long term and for it to indeed stay with us for the rest of time, it needs to allow some of the hosts to survive. So viruses that don't kill the host and viruses that can replicate and spread to other hosts are successful. And this creates a sustainable, successful interrelationship. And this is probably what we're facing with COVID-2. Now, let's come back. Most humans interact in a fairly reasonable way with this virus. It's no worse than influenza or a cold. Yes, we get sick, and yes, we do pass it on, and we miss a bit of work, we miss some school, but we do get better for the most part. And then it's probably going to come back a year later when our immune system has forgotten about it, and so this virus will go round and round and round. The difference between this coronavirus and the regular common cold virus is that some of us get very sick and die. And the difference between this virus and other coronaviruses is that this virus targets ACE2 and completely depletes the body of the ACE2 protein. So ACE2 depletion is really what makes some of us very sick. So we cannot understand this virus without understanding ACE2. And what is it doing there? And why do some of us have more of it, and why do some of us miss it when it's gone? It's a little bit disconcerting that over a year's gone by, and the ACE2 story still remains largely opaque and hidden and not talked about. I like to think this is not intentional, that this is literally manifesting as another silo of science that infectious disease specialists, epidemiologists, public health doctors know nothing about. It's a very advanced piece of biology knowledge and disease understanding that's largely dealt with by cardiovascular disease researchers. And I think we just have a problem here with communication, and that ACE2 is still baffling the viral infectious disease specialists, and we don't have enough crossover. The work around ACE2 is published. It's published in peer-reviewed journals. It's out there, but you have to know where to find it, and you also have to be able to understand it. So as of now, just as ACE2 has been around forever, and just as the Americas have been around forever, but were only discovered by Europeans. So ACE2 is now has been discovered in the last 20 years by humans, by scientists, but it's really been there all along, and it's about time that we now started to understand it. So ACE2 was first discovered probably in the late 1990s and was published around 2000. It was just a few years before COVID-19, which caused the SARS outbreak, broke. And so doctors at that time had no idea that ACE2 existed or what it did. We treated the virus as we would with any other H1N1 virus or a flu virus. And the death rate was startlingly high. It was really quite frightening. And in retrospect, looking back, that was probably because the treatments we used actually made things worse. And fortunately, that that little outbreak didn't turn into an epidemic or a pandemic, and it was contained quite quickly, largely because the larger dose of the virus mandated closer contact between humans. But most of all is that the immune response was activated early, and people got sick and started to have a fever and a cough before they started to spread the virus, so they could just self-isolate, lock themselves down, and contagion was contained. A lot of people did die, and some of those were healthcare workers, frontline healthcare workers who were the first victims of this virus. Once the virus disappeared, the threat did not, and virologists in the field continued to work with this new coronavirus, and researchers in the field continued to work with ACE2 to try and understand its role in human health. In the ensuing 18 years, for the virus to be able to come back and succeed, it needed to be more potent. In other words, it needed to spread more easily and require a lower dose and smaller particle size. And it also needed to improve on its stealth. It needed to get into its host and replicate and get out before the host got sick, and preferably have many hosts who didn't even know they were sick, and they could be silent spreaders, or so-called super spreaders. And so in essence, the virus needed to be trained to work in smaller numbers and to disable the alert system in our bodies long enough to get in, replicate, and get out. So, some 15 years later, with help from either evolution, it just happened, or with help from humans, the virus came back, perfected in the ability to create this pandemic, right? It's a little bit scary that this happened right next to a viral laboratory that was in fact perfecting this virus, or playing with this virus, right? Now, viruses constantly mutate whenever they replicate themselves. In other words, they don't make perfect copies. And that's almost a survival mechanism, because at times one of those imperfect copies may actually be an improvement. So the RNA is constantly being tinkered with, just naturally happens. There's no thought involved, but it's just constantly not perfectly made. And if there's an improvement, that one little virus, that one single virus that's better, will then survive the other viruses and will start to take over. And that's what we're seeing now. We're already seeing mutations which are labeled after different countries in which they were first discovered, but these mutations are occurring in every single sick patient by the millions, and we're going to continue to see changes in the virus. Now, these changes may not make the virus more lethal, but they certainly will make it a bit different. And if you're trying to teach your body to recognize the virus or the virus protein, the changes may allow the virus to, in fact, change its uniform and come in dressed as a different virus, and not therefore be handcuffed by antibodies, wrestled to the ground, and killed. So could this virus have made itself better for infecting humans while being in a bat, or did it need to go through human cells? And that's the research that's done around making viruses better at infecting a particular type of cell, called gain of function research, and that's where the virus is cycled through cells. And they watch closely by the virologists or the attending, the gardeners of these viruses, who will then watch and see if there's changes, what those changes are, and if the change makes it better. That virus can then be isolated and continue to run through human cells, and it can almost be nurtured until it becomes much better at whatever function that the nurturer or the person in charge of that virus wants it to do. So they really can be trained and can get a gain of function. Unfortunately, humans and viral laboratories do engage in this work, where they go and find viruses from far off animals that normally wouldn't bother us, and bring them back to laboratories, and then see how they can be manipulated. And this may be a result of that. So anyway, now we have a champion ACE2 virus, ACE2 killing virus, right? But we still don't know much about ACE2. And so we're trying to fight this virus with the usual techniques of sort of bland antiviral things such as stopping spread and trying to interfere with viruses as we would with any other virus, but without really focusing at all on ACE2. And the reason is that when it comes to treatment and applying treatments and knowing about ACE2, that relies on the medical community. And the medical community today is getting all of its knowledge from the infectious disease community, which doesn't know anything about ACE2. And so we have a mismatch. And because so much of our knowledge around this pandemic is being controlled and being managed, the voices around alternative treatments and alternative understanding of this virus are being suppressed. And so whenever you hear talking heads and experts saying how we don't know, there are things we don't know about this virus, we need more research, you could also substitute that with, I don't know about this virus, but somebody else might, and I just don't have the time or the ability to go and find out, and we won't allow those people to have a voice in case it's wrong. And so in order to keep a sound, solid message that is simplified and dumbed down, science is now unfortunately being curtailed to some extent, and this is the result. So let's get off that platform and go back. We're going to stick with the science. So what is ACE2? Why do we make it? What does it do? What system is it part of? And why do some people have lots of it? And why do some people miss it when it's gone? So the next podcast is going to be not focused on COVID and the pandemic, but it's going to be all about understanding ACE2. And then we'll come back in a third podcast and put the two together again. And then in a fourth podcast, we might look at the symptoms and causes of death and disease with people experiencing COVID-19 syndrome, as I call it. And even later on, we could look at some of the interventions that are being done and how they, in fact, can be explained through effects on the ACE2 system.